Here we are back again, and as promised, another practice problem which will utilize those uniform acceleration equations that we derived in a couple of videos ago. So let's go back to our situation. Remember, we had Becca and Sarah, and they were playing basketball together, and they were waiting for their ball to show up, and oh, sorry. Remember, we have to give them hands. So they're over there, and they're still waiting for their ball to show up. So it's rolling towards them. Well, let's say that the road is over here, and guess who comes racing along the road here in his sweet car? Oh, we got to block out the road there because there's a car in front of it now. And he's got a very, very nice car. It looks just like this. And he's in there, and there he is. And maybe I should draw his legs. There he is. And so he's got glasses on because he's very cool, and there's a steering wheel. So he's racing along. Now he sees these lovely girls, and he's definitely not one to pass up the opportunity to stop and wave at some lovely girls. And so let's call this guy in our car right here, let's call him Jacob. And so Jacob is racing along. And let's say he's racing along at an initial velocity of 44 meters per second. And so let's say that he sees the girls, and he wants to wave at them. And so let's say he slows at a constant rate down to 22 meters per second. And that's just about the perfect speed to stop and wave at lovely girls. And so he is he's slowing down. And let's say it takes him a total of 11 seconds to slow from his initial speed when he first saw the girls to his final lovely girl waving speed. So let's say that takes him a total of 11 seconds. And so, so how far does Jacob move during this time where he's slowing down to wave to the lovely girls waiting for their basketball? So, let's take a look and see what we know and what are we trying to find? Well, if we're trying to find the total amount of distance he moves during this time, what we're looking for is displacement. So the final question that we want to solve for is his final displacement. So what variables do we have? What do we know? Well, we have an initial and a final velocity, and we have a time. And so what can we do with that? Well, what we really want to do is solve for displacement. So the formula for displacement final, you remember, equals displacement initial plus the velocity initial times the time final plus 1/2 the constant acceleration times the time final squared. So this equation right here was the one that we figured out, which would give us displacement, because this essentially figures out the area under the velocity time graph that this particular situation would produce. So we have the initial velocity, we have the final velocity, and we have the time. So we have two variables, though, unknown. We have the acceleration is unknown, and our final displacement is unknown, which is kind of a problem. So first of all, we're going to have to figure out if there's a way to get one of these variables eliminated, so we could either substitute or solve to try to get it. Well, if we go back to our initial equation that we used in the last video for the basketball, velocity final equals velocity initial plus the acceleration times the time final. So we have the time final, we have the final velocity, we have the initial velocity, and so this would leave us with only one variable of the acceleration, which we could plug in here and then solve for our final displacement. So we should be able to do this. We should be able to figure out how far Jacob had to go before he could slow down enough to do his lovely girl wave. So, so let's go ahead and start plugging stuff in and seeing what we can get. So, so here we have 22 is going to be our final velocity, equals 44 is our initial velocity, plus our acceleration is our unknown, times 11 seconds right there. So I want you to subtract 44 from over here, so we're going to end up with negative 22 equals our constant acceleration times 11. So divide both sides by 11, we find out that negative 2 meters per second squared is our constant acceleration, or in this case, deceleration, because he's slowing down, right? But the negative shows us that. So let's go ahead and stick that in here, and then we can now easily solve for this. So our distance final is unknown. Our distance initial, since all we want to know is the total distance it took him to slow down, our starting point is going to be 0, because we're starting at 0. We want to know that the point that he saw the lovely girls that he decided to slow down and wave, how long did it take him, or how many feet, or in this case it would be meters, how many meters did he travel in order to get to his specific waving speed. So his initial displacement, or his starting point, would be at 0, right? And then his velocity initial, we know from before, was 44 meters per second. And his final time was 11 seconds. I'm just not going to write the units in here right now because it complicates it a little bit. And so then I have 1/2. And we now know that his acceleration, or deceleration, was negative 2. And our final time, again, was 11 seconds, and we're going to square that. So here we go. So now it's just a matter of taking this and solving it, and pretty simple thing for you to solve. So you can multiply these, subtract them over here, divide by 2, and end up taking a square root of something there along the way. So if you do all that, you will end up with our distance final is going to be equal to 363 meters. So just a hair over a football field is about how long it took him to slow down to waving speed. So maybe he needs to get his brakes checked or something like that, or maybe he needs to slow down. But of course the girls are impressed by his amazing car and how fast he can drive, so maybe he does want to go so fast that it takes him 363 meters to slow down. I'm not sure, but just sort of put this together real quick. Anyway, so that shows you actually how we were able to use 2 of those equation derivatives, which all of it comes out just from the simple constant acceleration equals change in velocity over change in time. And we were able to figure out all of this and learn a whole lot about this situation that we wouldn't have otherwise known. All right, hope that helps. And in the next video, we'll use the last and final equation that we talked about in the derivative. So each of those 3 we'll get to use.